Now our next speaker, while he wouldn't call himself Professor X, the work he is doing to help bolster resiliency for our Air Force fleet of aircraft is next level brilliant. The work that they're doing right now, forged to the fire, the crucible of partnerships, is showing how we can not only ask or really answer an age-old problem we've had in humanity of knowing when to strike when the iron's hot and how to take advantage of that. How's that being done? Well, Andrew Gilman's about to come up here and tell you with his talk, Striking When the Innovation's Hot.
What if we were in battle and couldn't manufacture guns or bullets, or parts to keep our air fleet flying? We're seeing the warning signs today with headlines like these: cascading issues keeping Air Force, Navy planes grounded. U.S. Air Force fleet's mission-capable rates are stagnating, and only a tiny fraction of U.S. military aircraft met mission-capable rate goals in FY21. Why are we struggling to keep our fleets in the air? The problem is similar to maintaining a classic car. Hobbyists do everything to keep these cars in tip-top shape for the car show, pouring time and money into them. But when that one critical piece breaks, you can't go down the road to AutoZone to get it. You've got to get creative in how you find that part. You may scour online dealers like eBay, visit salvage yards to find good parts from broken down ones, go to swap meets at the car show, and even consider custom ordering a part to be made by a machinist. All these take time, effort, and creativity. For Air Force systems, the underlying issue is a lack of agility in our supply chains and manufacturing systems to produce what we need when we need it. If the manufacturing system that originally made something is no longer in operation, we must pay in time and money for re-engineering. In order to dramatically change this landscape, disruptive manufacturing technologies are needed. I'm Andrew Gilman, and I'm working to transform brittle robotic systems designed for completing millions of repetitive tasks into machines that can adapt to new ones by the day. And my work has caused me to adapt as well. From a stationary life to that of a nomad researcher, I focus on embedding myself in expert beehives, where a large number of collisions occur naturally among leaders in the community. Before the days of assembly lines, we relied on expert blacksmiths to be our agile makers in society. They weren't just fabricating weapons and tools, but they were also repairing and maintaining them. Artisans have kept the craft alive through modern times, but we haven't relied on a blacksmithing concept to manufacture parts for our most exquisite aerospace systems. And while humans can be incredibly agile, there can be challenges in achieving the consistency and reliability that we require. But what if we had a reliable robotic blacksmith with the agility of a human? We could deploy these systems all over the world, where and when we need them. I'm part of a growing team of academia, industry, and government partners working to make the idea of a robotic blacksmith a reality. And I'm not just a team member from afar. I embed myself multiple days per week at a university lab, colliding in a vibrant and collaborative beehive with students, professors, and researchers as we work together and learn to create better technology faster. After all, our maintenance depots need these solutions quickly. The headlines introduced up front only begin to describe the situation we're in. Our fleets have average mission-capable rates of around 70%, meaning that 30% are in a state of repair and can't be deployed, and some are as low as 50%. As one of the lead automation engineers at our maintenance depots, Shane Groves, puts it, the main problem we have right now is that companies have plenty of work, and when I ask them for one or two parts, they don't see the return in tooling everything up for a small order. We're getting quotes for 4-year delivery times to get some of the right parts. This dilemma can leave our depots taking good parts from one plane to fix another, effectively cannibalizing one plane for the benefit of another one. How do we improve this situation and keep this from happening? How do we produce the parts that we need and the quantities we need quickly and reliably? To tackle this challenge of creating manufacturing systems that can produce in small batches, the team I'm a part of was formed 4 years ago, the Digital Manufacturing Research Team. We were tackling these challenges by exploring digital and robotic technologies, but with a limited budget and without a lab to start. Many of us in this audience know it can take years and significant funds to develop a new lab on a military installation. And it's hard to find critical talent at the intersection of robotics, artificial intelligence, and manufacturing. But we set out to build a vision and a team, but it was hard to scale up quickly. We put job ads out for robotics and machine learning engineers, but struck out time and time again and had not filled that role multiple years in. These challenges exist at the depot too. They couldn't always get well-integrated robotic systems to perform tasks well. Systems had been delivered, demonstrated once, and then placed in the corner to collect dust, given inadequate performance. I came to understand that this was going to take a unique assembly of resources, both people and infrastructure. We use our partnerships a lot at AFRL, but I wanted to explore a new way of partnering through active and routine collaboration and around a challenge that would unite people from government, academia, and industry. Towards this goal of creating a robotic blacksmith, I engineered my own Nomad Lab ecosystem to bring all of this together. As our team was growing, we identified an academic lab down the road in Columbus at The Ohio State University, just an hour drive from here in Dayton. The concept of metamorphic manufacturing, or robotic blacksmithing, had in fact been proposed by a group of experts in the US, many of whom were professors at Midwest universities, including Ohio State. And this lab had just received a consigned cohort of multiple large industrial robots, and the lead investigators shared the excitement for tackling the Air Force's challenges. But before we could begin to develop that prototype robotic blacksmith, we needed to understand the problem from firsthand sources. Since the existence of our team, I've made many trips to our partners at the depot, including one in Warner Robins, Georgia. I came to learn of components being machined out of large blocks of metal with lots of material waste. I learned of thin-walled structures being pressed from sheet metal that required significant re-engineering to get the process performing to many decades before. I shared these insights with our academic partners, and we collectively rallied around developing a system that could produce parts quickly using a robotic system. We iterated on the types of parts to start with and kept these sustainment engineers in the loop every step of the way. The first task were to replicate the critical aspects that a blacksmith does. We started with a forge press that you'll see in any artisanal blacksmith's workshop, and we added digital control valves and sensors to automate its operation. This would replicate a blacksmith's hammer strikes on a part lying against the anvil. We needed a suite of sensors to replicate the blacksmith's senses. A robot arm could take the part from the oven, put it in the forge press and deform the metal, but the arm would stop functioning if too large of a force was felt. So a sensor was added to the end of the arm to replicate a human's ability to adjust the grip based on the reaction of the part following a strike. We needed a heat source to increase the part's temperature, making it easier to form the part into the desired shape. So we took a standard laboratory oven and automated its operation. And we utilized an industrial 3D camera to capture the shape change over time. Like nearly all research and development, this system didn't come together smoothly. Sensors didn't always work as intended, and the algorithms for synthesizing the camera data to understand the current part shape weren't accurate enough at first to understand the changes being made. And one of the biggest challenges was to begin to replicate a blacksmith's mind. In other words, how would we take all this sensor information and decide how to strike the part next? This is where the true value of creating an active, collaborative beehive would really pay off. One person debugging a piece of code in the lab could quickly turn into all hands on deck. With the sound of the system turning on, we'd set aside our current tasks, put on our safety glasses, and gather around the robotic forming system to assess its current operation. We'd watch the system until it reached a roadblock, and then collectively exchange ideas on how we need to reconfigure the system or rewrite code. And then we iterated, collectively, until the system had formed the part's shape, as intended, autonomously, without human intervention. It wasn't just me, a Nomad researcher in a partner's lab. It was undergraduate and graduate students research engineers, postdocs, and professors engaging together in the same space, collectively deciding on the course of action that will lead to the successful development of this prototype. At the conclusion of developing this prototype system, I returned with the system and the team to Warner Robins Air Logistics Center in Georgia. Just as it had been designed to do in the lab, the system ran autonomously for multiple hours, incrementally shaping the part into the desired shape. This was deemed one of the most successful industry-academia lab partnership demos of its kind to be performed at this depot. Shane Groves, one of the key depot engineers who introduced the problem up front, said, "It's the way it was designed to work from the start. AFRL develops technology with the help of their partners, and then we help them test it, and then we transition together as a team into production." Shane usually recognized what a good partnership can create. He added, "The people who are successful are those who are agile and can adapt to changes, and the systems then have to do the same." In other words, it's people and robots working together that are going to shape our future technologies. The development of this system is just the first step in creating more and more types of parts. And since the initial development of this system, the speed is improving dramatically, and the number of partners is growing as well. A number of additional Midwest universities have joined Ohio State through a National Science Foundation program and has increased the amount of funding by more than 10 times our original project investment. And it's not just us in aerospace defense who are interested. Sister agencies in the Army and Navy suffer from the same challenges. In the medical field, sees a future of more customizable surgical parts that can lead to reduced surgery times and better patient outcomes. The robotic blacksmith is needed across industry sectors and will all benefit by sharing our challenges and solutions. Revolutionary manufacturing technologies, like the robotic blacksmith, show the promise of overcoming our grounded fleets. Because I work closely with our partners, we're able to develop a prototype system that can make parts on demand in the low batches that we desire. This effective collaboration proved that combining the collective knowledge of humans is the best way forward. So I invite all of you, find that partner who can help you in your work. Create a beehive of experts where we can help the warfighter together. I ask you, who do you need in your beehive? Don't wait to answer that question. Make a list right now. Start connecting with them and work to advance your technology area faster. Thank you.
I know we just clapped, but honestly, let's hear it again for Andrew, the Nomad Researcher Gilman. Truly amazing.